Hi everyone, my name is Colin Murillo and today I'll be presenting on the bending moment equation of a taper entasis column. This presentation is part of our differential equation course and I will be applying a mathematical modeling to a real world structure problem. Let's dive in. This is the problem I provided for presentation 3. I'll be using this problem from chapter 6, our learning objective. By the end of this talk, you will be able to divert a differential equation from a physical description to a taper column, solve that equation using an appropriate method, and interpret the behavior of the solution, specifically how the shape and the loading of a column affect its structure stability. Problem statement. Here, the problem. We have our problem here. We're given a taper adhesive column with the taper ratio that equals to 0.9 and a shape factor m equals to 3. It's subject to a constant axial force P. The goal is to derive the bending moment equation for this column and simplify it to the form shown. The key is to understand how geometry and the force interact in these systems. Imagine the diagram here showing the taper column bending under a horizontal axis, which helps visualize how these factors come together. For model derivation, let's derive the model. We start with the general form of bending moment equation from a beam, which the EI times the second derivation of y plus py equals 0, which is right here. The flexural rigidity of EI varies along the column is given in terms of x. Using the given shape factor and taper ratio, we compute EI as a function of x to the 2.7 power. Substituting this into our equation, we simplify and arrive our target differential equation with a variable coefficient that gives us the final form shown where lambda is defined in terms of P, A under O, E, and I under 2, which is right here. Solution steps. Now, solving this equation is challenging because it has a variable coefficient, specifically x, to the negative of 2.7. That means traditional methods for constant coefficient equations won't work. One possible method is substitution. I believe it would be substitution, like converting x to e to the t to simplify the exponent. Another approach which I will use is solving the numerically with Pythons using a method like Runicuta. Pythons always helps. This helps us understand the solution behavior even if we can get a closer form answer. Graphical and numerical illustration. I provided our graph right here so you can get a visual um, example of what I'm going to explain of our numerical solutions for different values of lambda, specifically in 1 to 10 and 15. These were computed using um, my numbers into the equation to provide the graph. As you can see, the behavior of our solution varies significantly with lambda. Higher lambda leads to more oscillation and more stiffness. This matches our expectations that stiffer column or one under greater axial force restricts bending more efficiently. Yes. Mhm. And this is my graph. I had to I use Excel for this. So I don't know if I have to provide it for my, what is it called? Um, my references. Interpretation and validation. Let's interpret these results as x increases or as we move along the column. The deflection pattern is influenced by lambda. Larger lambda means less deflection, which makes it sense because this makes sense because it corresponds to stiffer or more heavily load column. This is consistent with physical intuition. Stronger column bends less. Our numerical solution validates the derivative equation behavior and helps us understand its particle implications, which is right here, consistent with structure mechanics and expectations. Physical higher axial force P increases lambda stability in the column. Extensions, what ifs. Now, let's explore some valid let's explore some scenarios, some variations. First, if we increase the shape factor m to 4, the exponent in our equation increases to 3.6, which is like what I put right here, making the system stiffer. Second, if RHO is increased to 1, which is our ratio is increased to 1, we have our uniform column, which changes the behavior again. Both changes affect lambda, and in turn, the solution. We could plot these new cases to see how sensitive the system is to change in shape of material properties. Conclusions and takeaways. To wrap up, we derived, sorry, let me start. To wrap up, we derivative the differential equations for a trapped column, solved it numerically, and interpret the column and the solution. Key takeaway. Geometry and axial force strongly influence how the column bends to stay stable. This presentation shows how mathematical modeling helps predict structure behaviors aligned with our learning objectives. Questions and references. For my references, I used a textbook. I also had to read from it. I also used my homework, and I also used Pythons and Excel. I should probably provide that, but I'll provide it right now in a bit. Thank you for watching. The end.